I've got another electrical circuit. This time, I've got my power pack. I've got current flowing out the red terminal. It flows into the circuit. It can go one of two paths. It can go either around this way and back through the wire to the power pack, or it can come across this branch here and back to the power pack. This is called a parallel circuit because there are two paths, and we can see here, because they're nice straight lines, they're literally parallel lines to each other. That's how we can remember that this is a parallel circuit. I've got a bulb on each line. When I turn the circuit on, both bulbs light up, he says. Let's find one with better connections. When I turn the power pack on, both bulbs light up. We're going to think about the current and the voltage across these. So first, I am going to measure the current flowing out of the power pack. So to do that, I'm going to disconnect the circuit just here, where all of the current is coming in from the power pack. I'm going to reconnect it, running it through my ammeter, and we should be able to see, there we go, the circuit's connected, bulbs are lighting up. I've got 0.1 amps of current flowing through the circuit in total from the power pack. I'm going to call that I total. So here we go, I total equals 0.1 amps. Next, I want to measure the current that flows across this path of the circuit here. So I'm going to disconnect. I'm going to turn the power pack off for the moment while I do it. I'm going to disconnect just that path of the circuit. I'm going to hold my multimeter leads on, turn it back on again. Now across this path of the circuit, we've only got 0.5 amps of current flowing. And now let's have a look at what's going through the other path. Let's see how much is coming around this one. I'll do a similar test. Again, I've only got 0.5 amps. I'm going to call these I1 and I2. So let's put I1 equals I2 equals 0.05 amps. Why is this? Well, if we think about what current means, current is the number of charged particles going through each second. Remember, 1 amp means 1 coulomb of charge passing each second. If I've got 0.1 amps flowing through here, when it gets to here, some of it's going to go this way and some of it's going to go that way. The charged particles can't go both ways. So in this case, in this circuit, I've got the same amount going each way. It wouldn't always be the same amount going each way, but it would always add up to the total. So it's always true that I1 plus I2 will equal the total current. Let's make it clear that these are I's and not 1's. Oh, that is a 1. That's why we need to not be confused. Let's make that a 1 amp like that. There we go. So now let's think about the potential difference across this circuit. Let's see first the potential difference between where the current enters the circuit from the power pack and leaves the circuit from the power pack. I've got 13 point, oh, it's jumping around. Let's call it 13.3 volts. Oh, sorry, I'm measuring the wrong thing there. Let's try it again. I thought that was too many volts. We've got 4.7 volts. So I'm going to put here, across here, we've got V total. V total equals 4.7 volts. Remember, that's 4.7 joules of energy for every coulomb of charge that passes through. That's the amount of energy that they've transferred between here, going all the way through the circuit and coming back. So now let's see how much they transferred just coming across this branch of the circuit. So I'm going to measure it from here to here. Oh, it's still 4.7 joules per coulomb, but there's two. What? Okay, so if a charged particle comes along here, it's got to drop it's got to transfer 4.7 joules between here and here. It comes round and it's transferring all of them there. But what about up here? Let's put this here, V1 and V2. V1 is equal to 4.7 volts. Let's try V2, so see what V2 is. Again, let's look if it just comes around this path, so it comes from here, and it comes across to here. Oh, again, round it up to 4.7. V2 equals 4.7 volts. So why is this happening? How can we possibly have the same voltage when we've got two paths? Well, when a charged particle gets here, it either goes round this way or it goes across this way. That's why we saw that the current adds up on the two paths to the total. But each charged particle, regardless of what path it's got, is going to transfer the same amount of energy. So the amount of energy transferred per amount of charge will be the same on both of them. We've got fewer charged particles coming through, but each individual charged particle has got to transfer the same amount between here and here, whether it goes this way or this way. So that's why in a series circuit, we'll always see that V1 is equal to V2. Sorry, in a parallel circuit, we will always see that the voltage across one path is equal to the voltage across another path.